Well, good afternoon and welcome to another Reliability Roadmap online training session. My name is Terrence O'Hanlon. I'm the editor and publisher at Uptime Magazine and ReliabilityWeb.com, and it's my great pleasure to be your host and your moderator for today's online training. If you're looking for the training titled Mitigating Asset Failure Consequences Using Root Cause Analysis, you're in the right place. In this web workshop, we will outline best practices for determining the root cause and mitigating consequences arising from the asset failure or out-of-tolerance conditions within the framework of the PAS-55 Asset Management Specification. This will include discussion on the process steps, critical questions, key involvement, and recommended discipline to effectively and efficiently identify the root cause of a defect to correct or improve the condition of failing and failed assets. Today, we worked with APG to create 3 learning goals for this web workshop. The first is how root cause analysis fits into the PAS-55 Asset Management Specification. The second is an approach for identifying the root cause of failures. Third, an approach for handling root cause to mitigate consequences of asset failures and defects. Today, we're very fortunate to have Reid Jenner, Managing Director of Asset Performance Group, as our session leader. Reid's a senior leadership consultant who has designed and implemented enterprise-wide solutions in industries such as oil and gas, mining, power, and pharmaceutical. For over 20 years, Reid has helped major corporations in the area of root cause, failure analysis, risk assessment, project management, problem solving, and change management. In his current role as Managing Director for APG, Reid will help APG strengthen and refine its reliability practice offerings, develop structured work identification practices, and focus on customer solutions that address reliability needs and provide sustainable return. Reid will also help drive APG's efforts to develop and deliver education and the need for reliability and PAS-55. And a note for those of you who this is the first time you're on an Asset Performance Group web workshop, we've done a series of PAS-55 asset management related tutorials and web workshops over the past 2 years. APG has really taken a lead role in North America. They are endorsed assessors, and I'm sure Reid will talk about that a little bit, for the Institute of Asset Management, and it's just been a pleasure for to work with them in educating the Reliability Web and Uptime audience on PAS-55 Asset Management Specification. A few announcements before we get to Reid. If you have not already done so, please request your free subscription to Uptime Magazine. All you have to do is log on to www.uptimemagazine.com and click the subscribe tab. If you have your iPhone, iPad, or iTouch, just search the keyword Uptime from the App Store, and you can get a 2-year library on your portable device. Quickly, we have 2 training courses coming up at the Reliability Performance Institute, Maintenance Strategy Masterclass Level 1 with Terry Wireman, January 25th through 27th. Motor Electrical Predictive Maintenance and Testing Training, Jack Nicholas Jr. and Jeff Juralovich. More information about the Reliability Performance Institute trainings are at maintenanceconference.com. One last announcement, Reliability-Centered Maintenance and Root Cause Analysis, RCA, RCM 2012, March 23rd, 2012, at the Reliability Performance Institute. Again, more information online at maintenanceconference.com. And with that, it's my great pleasure to hand this presentation to Reid. Reid, here you go. I'm handing it to you, and I want to thank you for being here and sharing your knowledge and your experience with us. Very much appreciated.
All right. Well, good afternoon, everybody, and thank you, Terry. It's my pleasure to be here today to talk with you about something I'm very passionate about, which is using root cause failure analysis to improve reliability, performance, and results. So today we're going to be talking about what PAS-55 is and how root cause failure analysis fits within this context, in what situations RCFA is called for, how it can be used most effectively, and then we're going to summarize talking about some of the benefits and results we can expect when it is applied correctly. I think Terry did a nice little summary overview of who APG is, and don't want to add too much more there. Just tell you a little bit about us just very briefly. APG stands for Asset Performance Group. We're a professional services consultancy specializing in asset management solutions and advisory services for organizations across a range of industries in Canada, the United States, and Europe. We're an accredited PAS-55 assessor. And you can see on bullet 3 here on the slide, asset care is our proprietary term for the optimized whole life management of physical assets. So just a little bit more detail about who we are. So what is PAS-55? Lots of you may know about PAS-55. We've been conducting, as Terry said, a number of webinars over the last few months talking about the various provisions and uses of PAS-55. So just let me read you the kind of the first bullet here, and we'll just talk a little bit more about it. PAS-55 is the international reference benchmark developed by the British Standards Institution for the optimal management of physical assets, providing the definition of good practice in the whole life management of assets. And so really any organization that has significant investment in physical asset infrastructure has a critical stake in the management, the entire life cycle of those assets most efficiently, safely, and profitably. When we talk about the life cycle, we're really talking about the whole life cycle from selection and commissioning through the entire operational phase, maintenance and turnaround, all the way through to decommissioning and disposal. And a big part of this cycle includes RCFA, root cause failure analysis, to keep the equipment running at optimal capacity and returning it to full capacity whenever unexpected deviations occur. And so PAS-55 is a framework for helping us do that. So where does PAS-55 kind of fit in with reliability programs? Well, first of all, PAS-55 provides a common language and a consistent framework for various organizations kind of to use a consistent and best practices, if you will, methodology for asset management. It's a very rigorous and robust framework for designing and maintaining an effective asset management program. And it was developed in concert with reliability experts from a variety of industries with a view to optimizing safety, environmental, and operational results. As you can see here, official accreditation is available for organizations that wish to formally acknowledge their compliance with these standards. And this, in fact, may become more of a focus once the ISO adopts its coming 55001 standard, which is using the PAS-55 specification as its primary frame of reference. So I think we're moving more and more into kind of these standardized methodologies that have industry, broad industry recognition. And I think that's what PAS-55 brings to the table. So let's talk about what is RCFA. And if you'll permit me, I'm just going to use the acronym from now on. It's a mouthful, right? Root cause failure analysis. So we'll just go with RCFA for now. And here's a nice, tight little definition that I like to use. So RCFA is a process for determining the root cause of an asset deviation in order to improve or realign its performance. And so if we just deconstruct this sentence for a second, it's a process or a methodology, first and foremost, a rather rigorous, hopefully, process, as we'll see. It's designed to get to the root of the problem, the root cause. And the goal, ultimately, is to repair or return the asset to its previous state or desired performance. And so when we talk about root cause failure analysis, that's kind of the frame of reference that we'll be using, the definition, which I hope you find fairly easy to remember and fairly clear. So what does PAS-55 say about where root cause failure analysis should be applied? And they've got a few clauses in their specification, which, if you'll permit me this one time, hopefully this will be the only slide that I read to you. I'll just read to you these two sections. So section 4.6.2, the organization shall establish, implement, and maintain processes and procedures for the handling and investigation of failures, incidents, and nonconformities associated with assets, including investigating failures, incidents, and nonconformities to determine their root cause. Furthermore, subsection 4.6.2.1 states, the primary purpose of these procedures is to prevent further occurrence or escalation of such situations by identifying and dealing with the root causes. And so I think this is actually pretty clear, when we should use it and also what the purpose is from using root cause failure analysis in best practice asset management programs. And that is really to prevent further occurrence and to stop deviations which have already existed so that we can get them back up and running. So why is RCFA an essential part of asset reliability? And I think to me this is really the essence of it. Most reliability initiatives, in my experience, rely very heavily on forward-looking preventive analytic processes such as FMEA, RCM, total productive maintenance, etc. And so they should. I mean, of course, we're trying ultimately to prevent future failures and increase uptime and all that good stuff. But RCFA adds an essential and necessary element to reliability programs and practices because no preventive program, no matter how proactive or well-designed, can anticipate and prevent every contingency. What RCFA does is it corrects problems when and where they occur and helps to return an asset to its desired state as quickly as possible. In our experience, many organizations spend as much as 70 to 80% of their maintenance time and budget on corrective actions. And although proper and effective preventive predictive maintenance practices should bring this number down and move it more in the direction of proactive actions, unanticipated deviations will always occur. And so that's where RCFA comes in. We're using the forward-looking preventive tools such as FMEA, RCM, etc. And we're also using RCFA, which kind of addresses problems that occur in the here and now, or kind of backward-looking, that some sort of deviation has occurred recently in the past, and we need to fix it, right now in the here and now. Another use for RCFA, as you can see in the last bullet here, is whenever we have recurring problems with an asset, we can identify, predominant failure modes using RCFA, which will be used to help prevent future occurrences. So I think RCFA is a very powerful tool in an asset management program that can be used to address, problems when and where they occur, as well as preventing future problems in connection with our forward-looking reliability tools such as FMEA and RCM. So let's be a little bit clearer about when specifically RCFA should be used. So I think there's a number of conditions under which we might consider using RCFA. And first and foremost, whenever we have a priority condition or a deviation with an asset. So for instance, when something as simple as a light bulb goes out, of course, most of the time we don't really care about what the cause is, and we got a very simple fix. But if it's a more serious matter, like an overheating reactor, which is something I've had to deal with, this requires a more timely and urgent fix. And so we're going to use RCFA to address important deviations, asset or equipment failures, not minor or insignificant ones. Furthermore, oftentimes when we have a deviation or an equipment malfunction, the cause is known. It could be a recurring or a familiar asset failure, which we already know the cause for. And as a result, we may have a fairly straightforward or at least known fix for that. And so obviously if the cause is known, we don't need to use RCFA. It's root cause failure analysis. We only use that when the cause is unknown. Furthermore, bullet 3, there are times when we may have a deviation or an out-of-tolerance condition when it may be sufficient to address the symptoms only, not the cause. And so, for instance, if we have a minor leak of some kind of non-noxious fluid, that may be best to address, at least in the short term, the issue by just simply channeling the flow to some sort of overflow pond or reservoir. Or similarly, if you've got a flat tire, you just replace it with your spare and off you go. But if these kinds of problems recur, or if the consequences of failure become too high, eventually it probably makes sense to determine and address the underlying cause of the problem, not just the symptoms. And if you're a little bit like me, when you go to the doctor, perhaps you've seen this happen too often, a tendency to treat the symptom too quickly and not the cause. And I think that we all in the asset management space fall back on that. Sometimes it's easy to address the symptom, what we see, instead of digging deeper and addressing the cause. And the last bullet here is obviously, if we have a recurring problem and it's serious enough and it's been going on, or it recurs enough times and we just haven't been able to fix it or stop it from happening, I think we need to bring a more disciplined approach to prevent this from happening again. And so these are some of the circumstances in which I think RCFA is called for. Now, let's talk about the definition of a problem. And so a problem is a very specific type of issue that requires root cause failure analysis. So there's lots of different types of issues out there. I mean, some issues are decisions, require a choice to be made. Some issues are projects where we need to initiate some sort of program. Sometimes there's risks. But it's only these kinds of issues where we would use RCFA, what we call a problem. And our definition of a problem is when these three conditions, which you can see here on the slide, are present, all three of them. The first condition is we have what's called an out-of-tolerance condition with the priority asset. And what we mean by an out-of-tolerance condition is we have a deviation between what we want in terms of the performance of the asset or piece of equipment and the actual performance. So when there's a discrepancy or a deviation between the should and actual performance for a particular high-priority asset, that's condition one. Condition two is we don't know the cause. So as I mentioned earlier, obviously if the cause is known, we're going to take action, make a decision, or implement some sort of fix. We don't need RCFA. And the third condition, which is I think very subtle but interesting and important point, is that we need to know the cause in order to take meaningful action. And so I was working with a client some time ago, a paper mill, where they were having a problem with the beater pit overflowing. And when this beater pit overflowed, it contained a lot of pulp. They were basically knee-deep in pulp on the operating floor, and this was a very bad scene, as you can imagine. And this had to happen 3 times before the mill manager, felt it necessary to, bring a proper RCFA to bear to address the problem, which we did, and we solved it, and we'll talk some more about that a little bit later. Another situation, another client was a cement mill, and they had a repeating problem with the gear that was driving the conveyor belt on one of the lines, and one of the 2 teeth kept breaking on this gear. And so, after the 3rd time, and $15,000 or $20,000 replacing each gear, at this point we say, look, we need to know the cause. Why is this happening? So we can take meaningful action to fix it. And so we're going to say that a problem is one that meets these 3 conditions, and these are the conditions under which we would use RCFA. I believe, Terry, we have a question here for the group. Do you want to take over for a sec?
Yep, here it comes. What is the definition of a problem requiring root cause failure analysis? Is it that it's any unplanned stoppage of production? Is it an out-of-tolerance condition? Is it a deviation plus an unknown cause plus a need to know the cause? So just take a moment to indicate what's the definition of a problem requiring root cause failure analysis. Any unplanned stoppage of production, an out-of-tolerance condition, deviation, an unknown cause, and a need to know the cause. I'm going to give it about 5 more seconds. Got good participation here. And we're going to go ahead and close, and I'll share the results. Wow. 100%. I don't believe I've ever seen that on a web workshop before. 100% got it. No one said an unplanned stoppage of production is a definition of a problem requiring root cause failure analysis. Nobody said an out-of-tolerance condition is the definition of a problem requiring root cause failure analysis. Although 100% of the audience said deviation plus unknown cause plus need to know the cause is the definition of a problem requiring root cause failure analysis.
Well, Terry, let me just clarify. Can the group see my slide when we?
I can disappear the results here, and now they're seeing your slide.
Okay, that's good to know. Well, that 100% then is pretty impressive. I don't know if I should take credit for my clear presentation, but hopefully it was a fairly simple definition of a problem.
Absolutely, and I think it's really valuable to have that clear definition.
Yeah. Well, that's great. All right, let's move forward then. Okay, so how can we what are the tools or methodologies that we use to conduct a root cause failure analysis? Well, there's lots of different tools out there, and some of these are going to be familiar to a lot of the audience, I suspect. And so let's just kind of talk about some of these and how and when we can use them. 5 whys, for instance, which a lot of us are familiar with, helps to define the problem initially and also helps to ensure that the root cause is addressed. 5 M's, for instance, materials, manpower, machinery, methods, environment, and kind of an associated technique, fishbone, I find helps to brainstorm all the possible factors that might be playing a role in creating the problem. Apollo is another technique which helps to identify the collective set of influences which may be playing a role in creating the problem. PROACT is another technique which looks at both the physical and human, or what they call latent, causes of a problem. Kepner-Trigo, another process some of you may be familiar with, helps to specify the problem facts clearly and look for distinctions between a functioning and non-functioning equipment to help search for causes. And so there's lots of different techniques out there, and each of these methodologies has its place in RCFA. We use or select the appropriate technique depending on the nature and severity of the problem at hand. All right, so let's talk for a second about what's common to all of these methodologies, or at least a good, robust, effective root cause failure analysis. And these are what, in my 20 years of experience and what SAPG has found in its work with clients, are the critical ingredients for a successful RCFA. So first, we need to start with a very clear definition of what the problem is. And each of these bullets we're going to speak to in subsequent slides, so I won't go into too much detail. Number 2, we need to have a very clear and specific and complete and accurate description of the problem. And we'll speak to that in a minute too. It's helpful to have comparative data. What is being affected and what other similar pieces of equipment are not being affected. We'll talk about why this is very useful to have comparative data. One of the things that I find often we fall down in the process of conducting a root cause failure analysis is we often have very vague or general cause statements or hypotheses. And it takes a lot of work to get clear and specific testable hypotheses. And we're going to talk about that in just a minute. Another part of the challenge is to make sure that the evaluation of our possible causes is as objective and fact-based as possible, so we can minimize bias creeping into the equation and just running around spending a lot of time trying to fix things before we start evaluating them carefully and clearly. And of course, the last step, we need to confirm or verify or validate that we're right, that our conclusion is in fact the true cause. So, well, I see there's another question here, Terry. Before we go into each of these separate items in a little bit more detail, how about we have our second question here?
Here we go. Which of the following are critical elements successfully conducting root cause failure analysis? You need an objective and a disciplined facilitator. You need relevant, specific, and complete data, or both answers A and B. I'll just take a moment to indicate. Again, everybody's jumping on quite quickly, so we can get back to Reid here. I'm going to give it 5 seconds. And we'll go ahead and close and share. No one said an objective and disciplined facilitator by itself. 12% said relevant, specific, and complete data. 88% said both answers, A and B, an objective and disciplined facilitator plus relevant, specific, and complete data are critical elements for successfully conducting root cause failure analysis.
Yeah, and that's interesting. I mean, we haven't yet talked about the role of the facilitator, and as we'll see, it is a very important ingredient as well. So I like the fact that some of you picked up on that. But I think that plus the second item really are both required. And we'll come back to that a little bit later in the presentation. All right, so let's talk about this first step, problem definition for a minute. So the first step we feel in a good, effective root cause failure analysis is to state the problem very clearly. So this paper mill where I went to conduct a root cause failure analysis, the presenting issue from the team was beater pit overflowing. And as we talked about it at some length and clarified what the issue was, eventually we came down to a very different and I think far clearer statement of the problem, which was pump 2 fails to drain the pump well. Now, it took us almost an hour just to get to that point of clarifying what the problem was or what our problem statement was. And as it turns out, when we got to that point, the mill manager stopped, or one of the guys in the room actually stopped the meeting and said, hey, you know what? I don't think we need to spend 2 days in this room conducting a root cause failure analysis. I think I already know what the cause is. If you can just break for 10 minutes, I'm going to go check on something. And he did, and he came back, and we validated and confirmed the cause. And so just stating the problem clearly oftentimes can provide a great deal of clarity and direction on solving the problem. Another part of defining the problem clearly is making sure that we're dealing with just one object and one defect. In other words, one piece of equipment that's malfunctioning and one defect with it. So we don't want to say in our problem statement that pump A and B is vibrating. Let's separate those, especially if we feel there's a reasonable chance that each of those may have a different cause. It's a lot easier to solve one problem at a time than multiple problems. And so that's another step in the process in our problem statement. We also want to clearly define the defect. And so we don't say pump A is failing. We say pump A fails to clear the overflow from the pump well into the storage reservoir. And again, just being as clear as possible as a starting point. It may be useful also to define the so-called should and actual. If you remember our graph 2 or 3 slides back where we defined a out-of-tolerance condition and a deviation. What we like to call this, some of us only half kiddingly, is the should good and is the actual factual. In other words, we need to validate that our specification, our desired level of performance is attainable and reasonable. And we also need to make sure that we have good data to show that the actual performance is deviating from that. And so, for instance, if you have a truck that you're using in an industrial environment and you're expecting to get 70 miles per gallon, obviously that's unrealistic. And if you're estimating that you're getting 6 miles per gallon, I don't know, in an industrial setting, perhaps that is realistic, but we need to validate those two sides of the equation to make sure that we do, in fact, have a discrepancy or a deviation, because that was one of the 3 conditions for a problem. And that brings us to the next one. Let's make sure that we actually have a problem. I've run into so many instances where the clients are confused about what tool to bring to address the issue. And RCFA is the tool we use to address a problem as we defined earlier. If it's a decision or it's a project or some other type of issue, let's bring some other tools to address it. We use RCFA only to address what we call problems. And also, lastly, if there's a lot of problems on the table, let's separate those and just address, focus our attention on the most significant problem. All right, so once we've got a clear statement of the problem, the next step is to be very, very specific about describing all the relevant facts. And so we want to have, RCFA is only as good as the quality of the data that we bring, and in particular the description of the data. And so when we talk about quality of data, we're talking about the specificity of it. So for instance, I was working with a nuclear power plant some time ago, and they had a problem with a backup power generator. And we spent the better part of a morning just describing the defect itself. It was a subsynchronous type of vibration, very specific frequency and amplitude, and it took about a page to get it all down there and describe the problem. It was very, very specific, and that was very helpful in us solving the problem. We also want to be as complete as possible in the gathering and analysis of data. And so another problem that we worked on, we had rough patches on aircraft panels, but it was on 6 different panels, A, B, C, D, F, and G. Each of these panels having different configurations and manufactured on different stamping equipment. This was very, very important in us looking at all of these panels to solve this problem. We also want our information to be relevant in describing the problem. And so we want to describe the what, the where, the when extent. In other words, what specific piece of equipment is being affected and what specifically is wrong with it. Where is it located? Where on the piece of equipment are we having the problem? When did we first see the problem? When subsequently, et cetera. And so we want to make sure that we have the most specific, the most complete, and the most accurate and factual description of the problem before we begin to look at causes. Another thing that we found in our experience is very important in a root cause failure analysis is gathering comparative data. In other words, we don't want to just look at the piece of equipment that's malfunctioning or where we have a discrepancy deviation, but also if we can find some sort of similar piece of equipment that's operating in a similar operating context, this can be very useful in many ways. And you can see the bullets here in the slide, what this comparative data does for us. And so, for instance, just going back for an example here, going back to the paper mill again, another problem I worked on there was the paper they were making on this particular machine was tearing. But it was a very specific grade of paper only, not other grades of paper. Similarly, at the cement mill, where the gear tooth was breaking, it was only on line 1, not on 2 other very similarly configured lines. And so this comparative data, what it does for us is it, first of all, provides a basis for surfacing distinctions. And so these different grades of paper, for instance, had different paper machine settings, and the different production lines at the cement mill had different ages of equipment on each of the line. And these distinctions are very useful in helping us develop and focus our possible causes or hypotheses. The comparative data also tightens the is data. So going back to the nuclear power backup turbine, it was a very specific type of low frequency vibration they were experiencing, not a high frequency, a more expected high frequency vibration is what they were expecting. This was a very specific type of low frequency vibration. So it really kind of puts a box around and tightens our is data in terms of what is happening. The comparative data also helps us rule out possible causes. So for instance, in the case of the rough patches on the aircraft panel, you could pretty easily and quickly wear out the possibility of defective dye or mold on the stamping machine because 3 different presses all started producing the same wear pattern on different panels at the same time. And of course, the probability of 3 dyes wearing out at precisely the same time, the same day, the same hour is so infinitesimally small. You can pretty much rule that out right out of the gate. So having this kind of comparative data is very, very helpful. It's also helpful in evaluating possible causes that remain in contention by allowing us to have a more robust set of assumptions listed, which we can subsequently verify. And this kind of brings us to the step where we develop hypotheses. And again, this is an area that I find that very often we don't perhaps put as much effort in, or it's not as robust. And so one of the things that I found helps focus the development of hypotheses is to focus on these so-called distinctions. Because if a problem is happening in one particular place or with one particular piece of equipment, but never in another similar place or another identical piece of equipment, then there has to be something different about that unique thing, location, or timing to cause the problem. And in my experience, these distinctions, 95% or more of the time, is what leads us to the cause. So having good comparative data leads us to good distinctions, and having good distinctions leads us to good possible causes. Now furthermore, bullet 2 here, if we can further focus our distinctions on the most specific data that we have kind of a shorter list, if you will, of facts upon which to focus our hypotheses. So for instance, we're not going to ask where on the line or even where on the gear is the shearing occurring, but we're going to ask where specifically on the tooth is the shearing occurring. And when I asked that question at the cement mill, we found that there was a very specific kind of elliptical shape in which the tooth broke off the gear. And this led the subject matter experts to come up with a hypothesis. And we went back to the production line and made some observations and some photographs, and this confirmed what we suspected. And so again, focusing on distinctions at the most specific level of data helps us more quickly and more effectively find the root cause. Something else we can do under hypothesis development, we're not just looking for distinctions per se. Ideally, we're looking for changes in and around those distinctions, because if an asset is operating fine for a period of time and then suddenly begins operating unusually, something had to have changed to have caused that deviation. But we don't want to ask what's changed, right? Because there's too many things that change. You know, people change, and climate changes, and processes, and materials, etc. And so we really want to focus on what's changed around each of those distinctions. Those are the relevant changes. And that's a much, much shorter list of changes. And it's around those changes pertaining to the distinctions, which lead to the cause almost all the time. And the last bullet here, in the cause statement, the hypothesis itself, I've seen too often we have very vague and general statements, and we want to be as specific and clear as possible. So we're not going to say operator error or high rate of production. Instead, we should say something like operator inserts the blank into the stamping machine, thus scraping the edges against the die or the mold. Or perhaps instead of saying high rate of production, we could say the stamping of the panel too frequently keeps the die, causing deformation of the mold, which subsequently gets stamped into the panel. This requires a lot of work, which brings us to our next slide. The more specific the hypotheses that we develop, the more quickly we can evaluate them. So just quickly here, we're going to try to rule out the ones that simply don't make sense. And we do that on both sides of the problem description, the so-called is or is not. If it doesn't fit in one place, we rule it out very quickly. And so, for instance, I mentioned the defective dies. Just simply doesn't explain the rough patch in the panel, so it's gone. In step 2 there, the causes that remain in contention, we want to list all of the assumptions that we need to make in order to have that cause explain each of the sets of facts. And this provides a very robust set of data that we can subsequently evaluate and confirm. And plus, having this visible helps us identify the most probable cause, which is the one that has the fewest assumptions, or at least the most plausible assumptions. As we begin to evaluate the causes, there's 3 possible answers. You can see there in bullet 3. Yes, it does explain unequivocally based on these known facts. Yes, it explains only if we make these assumptions, which of course we're going to document and make visible. Or it simply does not explain under any circumstances because of these facts. If it doesn't explain, we rule it out and we indicate why. If it does explain, we keep it in and keep testing. That we list all of the assumptions that we need to make as we test the causes. And then ultimately, we're going to pick the cause that has the fewest assumptions, or at least the most reasonable set of assumptions, as our most plausible cause. The last step is to confirm the cause. And there's at least 4 ways to confirm cause. One is sometimes you just go look at it. And so, for instance, in the case of the paper mill, with the beater pit overflowing, the engineer went to talk to the operator to see if the recirculating valve was closed on pump 2 and found that it wasn't. And so basically we were just recirculating the pulp through this open valve on pump 2, and that's why pump 1 was having such a hard time clearing the pump well. And sometimes that's the easiest and quickest and cheapest way to confirm the cause. Other times you have to bring a little more sophistication. So in the case of the rough patches on the blanks, perhaps we have to have our vendor conduct some sort of lab test to make sure that, you know, using the same lot of defective blanks produces a similar wear pattern with a deep draw or a deep, stamping pattern. Other times we simply will remove the cause. Sometimes it's really simple to just remove the cause and inexpensive and to see if it fixes it. And so in the case of the paper machine, let's adjust the setting, which we suspected was causing the problem, and see if that has the intended effect on the tensile strength of the paper, which it did. And sometimes, you know, we can verify the assumptions. So perhaps we could call procurement and confirm that the change in the blank supply occurred around the same time as the defect was first noticed. So there's different ways to confirm cause, and we want to pick the one that's cheapest and surest, etc. Okay, Terry, how are we doing here? How much time do we have left?
We're doing great. We have 20 minutes left.
But we want to allow some time for questions, yes?
Yes. So we like to leave, I don't know, 10, 15 minutes, so about 5 to 10 minutes for your finish.
Okay, all right, we're getting there.
Okay.
So the essence of good root cause failure analysis boils down to good questions. And you know, we need a good facilitator. Somebody mentioned that as one of your answers earlier, to do a good job questioning. And so here are some questioning techniques that we found make a big difference. Questioning to the void means making sure we keep asking questions to make sure the data is as specific and complete as possible. We want to make sure that when we're questioning, we focus on our most specific answers when we look for distinctions. I talked about that earlier. We want to make sure that when we're looking for changes, we're not looking for all changes. We're looking for changes relating to the relevant distinctions. That's where the cause is normally found. And the hardest part, really, is how do you deal with the answers? I always say that asking the questions, the process questions, is kind of, anybody can figure that out after a while, how to memorize these questions. But the hard part is answering that, or dealing with the answers, because you never know what you're going to get. And oftentimes you get a very vague or incomplete or patently, false, incorrect, non-factual answer. And so we need to make sure that we engage the subject matter experts properly to ensure that the information is as good as it can possibly be. And that brings us back to the role of the facilitator, which is an incredibly important person in the equation, because the facilitator brings objectivity. The people that are close to the problem are too close to the problem, and then they've got biases, and often will run with it and spend a lot of money. The facilitator also brings a lot of rigor to the process. The facilitator provokes and probes and makes sure that we have the best data, and that data or information is being documented properly. It's not enough to have a good facilitator. You have to have the right people in the room that have knowledge about the equipment, and that may be operators. The ones that are closest to the problem often have the best data. Engineers, the designers, if you will, often have good data. Managers, you can see the big picture, and we want to have a balance between all of these. We need to make sure that we manage the group dynamics so that the vocal ones don't dominate or intimidate the rest, or that the quiet ones are drawn out. We want to make sure we have follow proper ground rules, keep everybody in line, and very important to separate the roles of the facilitator or process leader so that we don't mix them up. It should just be one process leader at a time in the room so that we only have one process at a time to keep us focused and moving forward. All right, just a couple more slides here, Terry, and then we'll turn it over to the group.
Okay.
So if we follow this process as robustly and rigorously and effectively as we can, here's what we can expect to see in the way of benefits. First of all, it shouldn't take long to do this. I had one client tell me recently that using their own process, it took them 5 engineers and operators, an average of 4 hours a week for 8 months to solve a production irregularity. And that's, I think, far too long. In my experience, sometimes it's just one meeting of a few hours, but certainly not much more than a week. It should be a week or less with a properly focused RCFA to get to the cause and thus, determine the appropriate fix. Another benefit of using RCFA properly is we get a very visible result. The asset returns to its previous operating state, and thus you can measure the ROI. You can measure the production loss from that lost asset downtime and the time and money saved from stopping that production benefit. That confirmed cause that we come up with goes into a database for future reference, for future troubleshooting of similar deviations, and also for building preventive actions around new failure modes. Some other benefits, the facilitator, the consultant or facilitator often gains significant credibility and trust with the client from having helped the team overcome a previously intractable problem. And lastly, a properly focused RCFA process helps to gather, organize, and evaluate information known or accessible by the operator or client. So we're leveraging client expertise. Okay, Terry, how about our last question here, and then we'll just have a quick summary and take some questions from the group.
All right, terrific. So what benefits does root cause failure analysis provide in a balanced asset management program? That it's a quality face time for consultants with key stakeholders. It's an opportunity for the consultant to bond with the operators, faster turnarounds on asset failures. Go ahead and give an indication. What are the benefits of root cause failure analysis provides in a balanced asset management program? It's a quality face time with consultants and key stakeholders, an opportunity for the consultants to bond with operators, faster turnarounds on asset failures. All right, I'm going to give it 5 more seconds, and we're going to close and share. Well, 3% said quality face time for consultants with stakeholders. No one said an opportunity for the consultant to bond with operators. 97% said the primary benefits in a balanced asset management program for root cause failure analysis, faster turnarounds on asset failures.
Right on. And I think that leads us kind of to our last slide here. We'll just summarize quickly here. So we'll go through some of these bullets just real quick. RCFA addresses a problem that has already occurred. It's a past event. It fixes it in the here and now, or the present, and it can help us prevent future recurrences by building more robust preventive practices around additional known failure modes. So RCFA really addresses past, present, and future elements within an asset reliability program. Also, an effective and focused RCFA process helps to find and fix asset deviations, when and where they occur, so that we can quickly turn around, as you mentioned in the last question. These new failure modes that we identify from an RCFA can be used to prevent future problems. They can also be used to investigate failing equipment, not just failed equipment, but any sort of irregular asset conditions, so that we can prevent further damage. Where, of course, all of this is designed to maximize production and equipment uptime. And so RCFA, in summary, it's an essential element of a holistic and comprehensive asset management program. All right, Terry, perhaps we can turn it over to the group, and hopefully there's a few questions.
Fantastic. If you have a few minutes to stick around, I hope.
Oh, absolutely, as long as you need.
All right, good. First, I think before we get started, Reid and I would like to thank the audience for their time and attention, especially their participation in the polls. That really helps Reid zero in his presentation, so we very much appreciate that. Also, one logistic is that this web workshop, as all the past APG PAS-55 workshops, have been recorded. We'll send you a link. You are welcome to share it with the people that you work with and any other stakeholders. We do recommend you come up and watch it again. You can find the past APG PAS-55 workshops by going to reliabilityweb.com, click on tutorials, and sort by the category asset management, and you'll be able to locate those. But this is being recorded for playback. There's a quick question about is there a North American equivalent to PAS-55? And in the interest of time, let me just jump in and say yes, it's actually becoming an international standard, ISO 55000. It'll be available to the general public late 2013. But it would be fruitful for you to start with PAS-55 right now, and you can go to APG's website, and there's a lot of information about PAS-55 up there. The ISO 55000 that's coming is not going to be a huge step change from PAS-55, so if you worked with somebody like APG to put in the framework for PAS-55, you would be almost all the way to an ISO program anyway. Sorry I jumped in and answered that, but I wanted to make sure that we got clear on that. How is root cause failure analysis a forward-looking reliability tool when you do it generally only after a failure occurs?
Yeah, that's a really great question. And I think, to be clear, it is really mostly designed to address a past event. There is a deviation, something has happened, and a piece of equipment has malfunctioned. And so the primary use of RCFA is to address a deviation that has occurred sometime recently in the past. The use that it can take for addressing future issues is really to identify new failure modes that we can build into our forward-looking asset management practices, such as RCM, to build more robust preventive actions around this new failure mode that's discovered from RCFA.
That's a great point. If there's a chain of problems, can you still use root cause failure analysis to get to the causes?
Yeah, and I think that's where Apollo kind of comes in a little bit too, trying to look at the multiple influences or factors or causes that play a role in causing the problem. In my experience, usually it boils down to ultimately one sort of trigger or one event, usually an environmental condition of some sort that is the root cause of the problem. So yes, absolutely, RCFA addresses really any deviation where the cause is unknown, regardless of how complex or the multiple influences that come into play.
What if there's not a similar equipment? In other words, what if the equipment's all different? Is there any
That's a really good question. I remember I had to deal with that once with a client. It was, if I remember correctly, it was a mining site in British Columbia, and they had I won't bore you with all the details. Anyhow, they didn't really have, it was a very unique and complex setup, and they didn't have anything similar on site, nor did they have any at any of their other sites, and nor could we even use competitors because it was such a unique thing. And so when that happens, what I have found useful is to refer to kind of the design specs for the piece of equipment, and use that as our frame of reference. And when you look at how is our equipment configured versus the intended or design specs, oftentimes we'll find, as in the case of, when we put together a barbecue, I'm sure we've all been there, and we make mistakes, like, oh gosh, I forgot to put this bolt in the right place. So again, it's tougher, and it takes a little longer, but you can still absolutely get to the cause by bringing a few extra subtleties into the equation.
Does or should root cause failure analysis stop at the physical causes, or do we need to continue the process until we find the system or the systemic causes?
Yeah, right on. Great, great questions. Well, what we've talked about primarily in this webinar is getting to the physical cause, or basically where is the malfunction on the equipment. But ultimately, I think one of my colleagues said it always boils down to biology or physics, which is the root. So it's either a human or some sort of environmental issue. And so yes, when we find the physical cause, so if we find a piece of equipment is damaged or there's an environmental issue, well, really more the former than the latter. What human influence or behavior was instrumental in either not detecting it or laying the foundation for creating it, because we do want to stop it from happening again. We don't want to fire people or hold people responsible, but we do want to get down to the latent or human root that led to this problem so that we can prevent it from happening again. Absolutely.
Did you mention the cause of the problem with the generator?
Wow, that was a really complicated, if you want me to, I can pull up the, it's a very long, but basically it was an overheating of, let me see if I remember now, it was an overheating of an electrical generator which caused an expansion of the metal. And there were two turbines that were facing each other, and the combination was driving this drive shaft to create the power. And it was the overheating in a particular electrical device near the turbine which was causing an ever slight change in the positioning of the turbine. And that is what was causing the vibration.
Wow.
I know, it was an unbelievably complicated analysis. It took about 5 days. We had the manufacturer rep on site. It was really interesting. I was tempted to show you some of the level of detail that we brought. It was really incredible.
Well, what a great find. Who has to be trained in root cause failure analysis techniques? Is it just the facilitator, or do the people participating also have to have some training?
Yeah, right on. Love these questions. Well, I'm going to be a bit of an outlier here, a bit of a rebel, and say that really I'm not sure that all of the subject matter experts or operators have to be trained. The most important person is the facilitator. If the facilitator is good, and the facilitator asks good questions and brings a very rigorous process to bear, it's my personal belief, after 20 years of doing this, that the people on the other side of the table don't need to know the process. It helps to outline at the beginning what the process is so they can just kind of follow it. But their job is to provide good data, to know the equipment. That's their job. The facilitator's job is to know the process. And I actually like to keep separation between the content and the process. And so you might even make a case that we don't want necessarily too many of the other folks in the room to be too familiar with the process, because they'll want us to take over for the facilitator and start leading, and that leads to all kinds of trouble.
That makes sense. Is there an optimum number of people for the root cause failure analysis team?
Yeah, and again, that's a tough one. Of course, I got the really awful consultant answer. It depends. It depends on the severity. It depends on the complexity. Like, for instance, the paper mill beater pit overflowing problem, I asked for and got these people in the room. I asked for the mill manager to be there. I wanted the engineering manager, the manufacturing manager, the maintenance manager. I also wanted the operators there. I wanted some design engineers there. And so, because that was a big problem. It was the third time it happened, and it was just, we needed to fix it. Other times, if it's smaller or contained, the nuclear power, the backup power turbine, I wanted a manufacturer rep in that room that was intimately familiar with the design of the turbine. So I think the important thing is that you have subject matter experts in the room who collectively are going to be able to answer all of your process questions. That's the key. And once you know what the process is and what the process questions are that you're going to ask, I think it's a lot easier to figure out, who can answer those questions and assemble that team before the meeting begins.
Excellent. Well, very, very good. Well, very interesting to do this in the context of PAS-55, certainly a critical element. For those who are interested in the PAS-55 asset management specification, even though it's a British specification, there are lots of North American companies that are building the framework around it. And the reason why they're doing that is because ISO, the International Standards Organization, is working on an international standard to replace PAS-55. So, and I'm on that committee, so I can give you a sneak preview that it's not a huge step change away from PAS-55. It's a small step change away from PAS-55. So it would be a good idea to get up with APG and discuss with them what PAS-55 is, how it can help you in all these various areas. We've done previous web workshops on risk analysis and other elements related to asset management and reliability. Be very valuable for you. So it's APG. Is it apgassetcare.com, Reid? I can't recall the APG, like Asset Performance Group, apgassetcare.com to get up there. They've linked all the PAS-55 web workshops from their website. You can also get them from reliabilityweb.com. Go to tutorials, sort by the category asset management, and almost all theirs had PAS-55 in the title. This one will be both there and at the root cause analysis category. Sorry about that, stumbling a little bit. Well, once again, I think Reid and I would like to join to thank the audience for their time and attention, and I agree with Reid completely. Fantastic questions, very illuminating questions at the end of this web workshop. And we'll be sending you a follow-up with a link to APG's website so you can get up and visit them. I think the audience would certainly like to join Reliability Web and Uptime Magazine to thank Reid and all the folks at APG for bringing us this educational web workshop, plus the past educational web workshop series that you've been doing on PAS-55. We all very much appreciate the leadership you guys have shown in North America for bringing PAS-55 to the forefront, and I hope we can get you back here to do some more in the future.
Absolutely. Thanks for having me, Terry.
That is our pleasure. This is Terry O'Hanlon, Uptime Magazine and Reliability Web signing out. Everybody have a great day. Bye now.